Can everyone hear me? Oh, okay, perfect. Right, so hi everyone. As Becca stated, I am Supriti Vijay. I'm a grad student at Carnegie Mellon University. And today I'm going to be talking to you all, or basically giving you like a quick tour of how you could iteratively identify code, vulnerable code in code bases. This tagline, reason, search, retrieve, repeat, isn't just a tagline. It's basically what every single security analyst does. Basically, they start off with a suspicion, they reason, they search, they find 100 irrelevant things, and then finally find that one bug or one vulnerability after maybe their 100 grep command and like 3 cups of coffee. And yes, I'll be taking you through how we can automate this entire process. This work is in collaboration with Cisco Foundation AI. My co-author Aman is sitting right in the front. If you have any questions afterwards, please feel free to catch us up, and we'll definitely take you through it. Right. So before, let's like talk about what I was mentioning before. We have so much vulnerability intelligence data over here. We have CVE databases, we have GitHub security advisories, we have OSV databases, and we even have like a NIST maintained vulnerability repository. So on paper, we should be very well informed, right? But say this is you sitting in some organization and going through the organization's large code database, and then you realize that you feel clueless on how you can connect this intelligence as well into, say, your code base, right? So you kind of feel super clueless about this. And then you see that you have this gap, and basically there is no bridge on how you can connect, say, the intelligence that you find online to the code vulnerabilities that actually exist in your code. Now, you would say that, well, we have static analysis tools, right? Yeah, we do have grep, and it definitely works, and it definitely helps. Although this is limited and kind of only limited to known patterns. So think of this, you're on a beach, you only have a metal detector that apparently hides, like only beeps the coins that you've already seen before, right? It's definitely of no importance, because what if some new coin comes into the picture, or you find like the same bug in some different syntax, then the detector kind of goes silent. And on the other hand, you have human security analysts, which are amazing at this because, well, they find these vulnerabilities across all of these repositories. But this is like hugely a manually driven process. It's super time consuming and lengthy. Let me give you an example. Say you are a security analyst and your mission is to find this vulnerability code chunk in a 2 million line code base, right? So this security search problem now converts into a security search nightmare. And basically you're searching through SQL injections, user input validations, and maybe, just maybe 6 hours later, you finally find that one bug and you create your prepared statement, which is a huge understatement because it usually takes a whole lot time longer than that. Now, what if I could tell you that LLMs could really, what if they could search in just a few seconds, right? Let's see what the current approaches kind of say on this. So first of all, the problem with a lot of these methods is lexical mismatch. Now, what I mean by this is that not all of the code kind of fits, say, the same way. Now, you would expect that writing and executing the code has like different kinds of logical formats. And just what you're trying to say may not be represented in the same format. The second thing that I'd like to highlight is semantic modality gap. Now, the dialect in which language is spoken and the dialect in which code and security is spoken is quite different, right? So words with negation, like how do you even write this in code, right? Unsanitized, how do you even represent this in terms of semantic modality? Because it would just probably capture sanitized or unsanitized, and this would probably never come into the picture. The next would be, you would say, you could probably go towards retrieval-based formats, right? Maybe look into like once you've done semantic, you could go into RAG-based formats. But the problem with like single shot query retrieval is basically the fact that there is no backtracking, right? It's just a one-shot retrieval-based method that basically gives you certain retrieval vulnerability code chunks, which may not actually be it. So it's locked in. And the third could be something that's new, that's query decomposition, is that you could either break CVEs or CWEs into, say, multiple steps and try to evaluate with that. But while this may work some of the times, but you are assuming that your entire LLM kind of already knows the repository really well and the structure of the repository really well. Right, so this leads us to our research question, is that can we teach models to really search like security analysts, iterating and refining through these hypotheses? And well, this is our approach to the problem. Our solution was iterative vulnerability retrieval, right? So let's think of an ideal scenario here. Here you have like an abstract user query. And how do we begin with this, right? Maybe our turn one would be taking some keywords from the search query and then looking at the retrieve top K. And then realizing that maybe Kafka is going to lead us to something, right? And then you would probably go into turn two, where you would see that, okay, Kafka messages, you like alter your search query, and then you get your new retrieve top three, and then you're still not satisfied because you still haven't found your vulnerability here. And then maybe you realize that maybe pickle is the hypothesis that you're chasing, right? And then finally, when you change your query to pickle loads message value, you notice that your first top three finally contains the vulnerable code segment. So ideally, we're looking into a system that can iteratively converge towards the target document, right? Now, in order to do so, how do we create like a perfect iterative vulnerable search data set, right? How do we go about doing what we planned an ideal system would do? And in order to do so, we look at raw GitHub security advisories, which basically contain vulnerable code repositories. And we scraped all of this. So this had like 300,000 GitHub security databases, right? Vulnerable code databases. Now, out of this, only 23,000 were actually verified reports by the GitHub security team. And out of that, only 9,542 had linked and legitimate repositories part of them. Now, we would kindly consider 9,542, but then we realized that only 4,702 repositories actually had verified vulnerable code. Now, what I mean by this is that they actually had proper issues and like proper PRs that were linked to those issues, and they were resolved through those PRs. And basically now we have a system where we know what the vulnerable code segment is, what the vulnerable code chunk is, and that's how we're going towards maybe approaching the problem. And now out of this 4,700, we realized, so we went deeper into this to like analyze the kind of repositories that were there. And we noticed that the first 100 and 200 repositories just had like data sets and binary files, which apparently were consuming so much storage, right? So what we basically did then was that we removed them because we thought it wasn't relevant to our cause, because we were looking for more vulnerable code segments and like code data in specific. And we realized that all of these code changes were actually part of one file, which was super convenient because then it kind of limits the number of relevant documents as to just one, right? And then this led us to a final data set which had high quality samples, which we then divided into 4,000 for trading and 500 for evaluation. And these evaluation data sets, we made sure it was the largest repositories possible, so our model actually had the toughest problems that are out there to end up solving. Now, to go more into the statistics of our data set, because we created it, we realized that not only was our model performing or going to be exploring just one particular language or one particular ecosystem, it had multitudes of them. You can see Java apparently in GitHub repositories has the highest number of vulnerable code data, and like the ecosystem's PyPy package has apparently the most amount of vulnerable code segments. Now, a couple more statistics. We wanted to understand what was the random chance of success, right, of like finding these vulnerable code segments. And we checked this out, and we had like about 7,808 code chunks on average per repository, and that was a 0.064% chance per search. So, which is basically nothing, right? It's not statistically significant even. It's not even a 1% chance. Now, how did we approach this problem, right? So we started off with a base model, and we did this in three main stages. One was making sure that the model had some security knowledge so that it could understand what a vulnerability actually is, right? And second was that to ensure that we could somehow get the model to learn how to search really well, right? Understand what vulnerable code is and understand how it should begin its search process like a security analyst, backtrack, refine its hypothesis. And third, using some kind of reinforcement learning method that would somehow reinforce or double down on the knowledge that it had learned before. So basically, and ideally, we're looking at a system where, given any user query, we would then look at the model being able to think, being able to search, and then being able to retrieve. And somehow, we realized that it has not retrieved the right thing. So it would go refine its thinking process, its search process, its retrieve top K process, and then finally give us a target top K retrieval. Now, in order to go into details of our methodology, in order to instill and distill security knowledge into our model, we took a handful of Wikipedia articles which had CVE, CWE IDs, and just so that it could understand the bare minimum of what security basically is. And then we added behaviors and search behaviors that I talked about. And this basically expanded across three basic things that we thought every security analyst does. It starts with exploration. So it goes to the breadth of topics that could probably exist, breadth of hypothesis that could probably exist, because there may not be the best perfect way to go about doing something, right? And then exploitation, go deeper and refine one particular hypothesis really well. And backtracking, which is super essential for a high-stake domain like security, where you realize most of the time that your first hypothesis may not lead the best kind of results, right? Now, moving on to the reinforcement learning part of this, we kind of redefined search as an RL-based task. So we created a simple environment to do so. And the way that we did it was, given an abstract user query, we have our top K responses, right? When it makes a call to the database, a simple reward structure over here would just be if the target document is present in the top K ranked responses, and second, if the target document is not present in the top K responses. So we're looking at a binary reward system. And in order to make them more granular, what we did was that we used reciprocal rank over the entire corpus, which is basically making sure that the higher or the most relevant document is part of is more higher on the ranked list that we're getting in. And we also use cosine similarity between the user query and the target document to ensure that it's semantically also similar. So we use multiple rewards over here. And to talk more about the kind of RL optimization we used and to give more background on this, we use something called as GRPO. I don't know if everyone's aware of this, but it was recently used by DeepSeek as well. And basically, it stands for Group Relative Preference Optimization, which basically means the fact that you're operating in a group of the model producing certain samples and then aligning the behavior of the model towards positive samples and steering it clear from negative samples. And so basically, let's consider this formulation. And over here, one block stands for think and search queries. And so we have multitudes of blocks that the same model produced. And we calculated rewards for each of them. And we want to now steer it towards the positive sample. So we're taking the highest reward. And that becomes our context for our next turn of search results that we'd like to go towards, because we want the model to understand how it could refine its hypothesis. And we give it a maximum of 5 turns, 5 chances to reach its ultimate goal. That is the target code chunk. And this is what you can see turn 2 is. Once it's selected block 2 as its context beforehand, as the hypothesis that it wants to go deeper into, it then goes into block 2.1, 2.2, 2.3, which is a consecutive think trace and a search trace based on the first think trace. And then we have more rewards that are created. And sorry, oh, can I go back? Yeah. Multiple rewards of the search traces that are created, and that is how we continue through the 5 turns. Now, let me give you an example of this is a model actually in practice of what it was given and how it basically delivered all of its results. And here we have the user query where this was the input that was given to the model. I've been looking into potential security gaps in our Python project's version control. Are there known issues with how parameters are sanitized in this context? Not looking for template files. Right? And then the thing you could see is actually short. It's like looking for parameter sanitization. It's bringing in keywords in and validation patterns in Git operations. And then the search query is based on the think, and it's delivering like some top tier responses where you see the model is able to interact with its searches and its responses and think, where it's like it found some validation functions, but it needs to check for sub-process execution patterns and potential shell injection vulnerabilities. And this leads it for its second search query, where it realized the single shot retrieval doesn't really work, right? And the second search query, which results in the next top tier response, is where it finds its vulnerable code segments. So you can see the model actually came up with all of this, right? And given just a simple input user query. Oh, sorry. Right. So I know this is the slide that everyone's most waiting for, the results section. And I'm really happy to show this. We started off with really compact models, 360 million and 1 billion parameter models, and we were able to show really well performance. I mean, we're not the best, but we're still out there. We have competitive performance. And a 1 billion parameter model, something to note over here, is competing with like 400 times and like 200 times its size over here. So we're looking at like small compact models performing really, really well. And I don't know how many parameters 4.1 is, but I'm guessing trillions or something. But you can see how it's giving really good performance. To talk more about the metrics here, success rate basically stands for whether the target document was present in the top 3. And you can see success rate over here, it kind of defines whether it got it right in any one of the turns. So any one of the 5 turns, and you can see how it's performing really well. So about like 43.9%, and you can see how small LM2, which is just a 360 million parameter model, is performing like 40.3. So all of our Argus models are performing really, really well. And to move on to the aberrations, just to see whether our methodology really worked well and what we were actually gradually leading the process towards, is that the base model, when we started the Llama 1 billion parameter model, only had a success rate of 19.6%. And our SFT security, after we added the security knowledge to it, it did boost performance because it then realized what vulnerabilities are, and that led to 27.7. I think just to take a pause over here is that this kind of reinforces why it's important to use security-based models for security-based tasks, and why general models do not really work that well as well, right? And then it moves towards SFT search. When we instill it and teach it how to search really well, that boosts performance by a lot. So it's basically teaching it how to search like a security analyst. And our GRP or RL algorithm also pushes this further to like 43.9%, which is our final performance. And then we have something I want to note in all of this is average successful depth, which is basically the fact that compact models you would have thought of would be like, while it's super fast and the latency is really great over here, right? Where the latency is better over here, you would notice that you would probably assume that it would take more turns to answer the question, right? Because a bigger model would always be better. However, you notice that it's able to refine, and like in just 1.68 turns, it basically gets the right answer, at least for the Llama 1 billion parameter model. For the small LM, it's at 1.6 as well. So it's quite similar, but like almost 2 turns. And you can understand why single shot retrieval doesn't really work that well, and how just giving it another chance to answer the same question and like refining its hypothesis, interacting with, say, the retrieve top K, gives it a better chance to understand and like kind of reinforce and like find these vulnerable code segments. Now, some of the search behaviors that we observed was first keyword refinement. That over here, something that we observed was that it's always started with models always taking keywords from the user query, which always starts with like broad queries. This is also assuming that the user knows what he's talking about and is not talking in a very vague language over here, right? So we notice how models kind of refine these keywords over turns and move from like broad to more precise queries. That was something that we noticed. Another thing that we noticed was adjusting the scope. So when there was query something in terms of like URL path traversal and like path handling, it started with like URL path handling. It then went towards path validation error conditions, which was problematic. And then it was able to pivot to a better hypothesis and then move towards directory traversal error handling, where it got it right. So not only is it creating hypothesis, but it's also pivoting and like backtracking its way through it. Third is context integration, something that it's doing because it's like an agentic system at this part. It is interacting with the responses it's getting. It's thinking its way through it. It's searching and it's creating much more refined and like better, precise hypothesis towards their end goal. We notice over here is that after seeing session.py in turn 2, in one of their hypotheses, it changes its direction to JWT token expiration validation, where we see it's not only integrating context, but it's also integrating all kinds of knowledge and like thinking processes into its process. Yeah, to conclude, I would like to conclude with like three main things over here. One is the fact that strategic search definitely works better than static patterns. So models definitely learn refinement strategies and they just don't like match simple static tools, simple patterns as well. Second is that 360 million or 1 billion parameter models definitely match 200 billion models. I'm sure all of us have really good resources right now, but definitely using smaller and compact models definitely matches these really big models as well. And not only are they edge friendly, student friendly, mobile friendly, and every kind of friendly that exists, they're also really cheap. Third is RL environments enable AI for security. I think this was stressed upon a lot in yesterday's session as well, and all the amazing talks that were there. But I think I'd just like to reiterate on that RL kind of definitely enables adaptive exploration and definitely gets the model or gives it an environment to really explore and exploit at the same time. Thank you.
Hi, is there a mechanism for the model to report no results? Like, for example, if you search for some data and it doesn't have any of the relevant abilities?
I'm sorry, I didn't hear it in the middle. Yeah.
Is there a mechanism for the model to report no results in the top K? Just for example, if there was a repository that didn't have any of the relevant security vulnerabilities?
Right. So in this, because we made sure that we use GitHub security advisories and our data set contain mostly vulnerable code segments. We didn't really have that kind of case because there was always one code chunk that was vulnerable. But I'm sure if we like extended this project, we would definitely do like other repositories and like to find vulnerable code segments in like normal repositories and give it those kinds of data sets. We would definitely learn that as well.
So false positives in this instance would just be them reporting in the top K something that's not relevant?
Yes.
Okay, thank you.
Thank you.
Hi, great. First of all, great job. I loved it. A quick question regarding the search. So if you have multiple, or the result is like really big regarding the top K, how do you deal with context window? Because well, smaller models struggle with big context.
Yes, for sure. This limitation did exist. What we did initially was that we divided all of our repositories into chunks, the way that RAG handles it too. And that's how we went forward with it. So based on the context window that was present for the small, we just divided into chunks. And that's how we tackled it. But this is definitely an issue, a limitation for smaller models and even larger models, to be honest. But yeah, this is at least how we approached it, just dividing it into chunks.
Like, would you say like similar size, like let's say 4,000 tokens?
Yes.
Okay. Thank you.
Yeah, thank you.
Thank you for the great talk. Could you talk a little more about how the user query is constructed?
Yeah, for sure. Sorry. Okay. Can I go ahead? Yeah, thank you. I am just going to show you the example ones. Oh, just a minute. I'm so sorry. Oh. Right. So basically, the way that we've constructed the user query was using GitHub Security Advisory. There were issues in which they labeled like exactly what vulnerability or like what issue was going on. And what we did was that using like an LLM, we kind of augmented them into like as many vague queries, and like we distributed them on like a scale of vagueness and asked them to like write it in more like natural language where people could would talk about the particular vulnerability in like different kinds of vague queries. So like we kind of distributed it over the vagueness, but we used an LLM to kind of augment and synthesize them.
Thank you. Just a follow-up. So the user query already kind of takes into account that it's looking for a specific vulnerability that you know that is there?
Yes.
Thank you.
Thank you.
So I got a question from Slack, and so did you do an ablation study with GRPO only, and how significant is SFT for doing GRPO?
So we did not do it with just GRPO because we started with a base model, and if we would have just done GRPO on that, we believe it would not have understood security relevant terms, and it would not have actually learned how to search really well, while just GRPO does work when the model does have like, so basically what GRPO and like RL optimization methods do is that they do not induce new capabilities, but they kind of double down or reinforce on what it has already learned, or like find patterns in what it has already learned. So we needed it to first have like a foundational understanding before we could have done RL optimization.
Thank you.
Hey, great talk. Really impressed by your domain adaptation results for the initial SFT runs. What was the token size to adapt to security, and how did you format those for that run?
When you mean by token size for security, do you mean how big the data set was?
Yeah, SFT domain adaptation.
So I think it was just 10,000 samples, and we basically extracted all of Wikipedia and for like security, and like reduced them to like 10,000 samples of those. I think token wise they would probably be a bit more, but in terms of like data points, it was like about 10,000 samples.
Awesome, thanks.